So the purpose of this video is to talk about lesson 3, but before we begin with that, I want to map out where we've been, and so we can sort of better appreciate where we are, where we're going. In lesson 1, we talked about resonance. We talked about resonance contributors, resonance hybrids, and electron dot structures and so on. Resonance was the issue for lesson 1. For lesson 2, that really automatically ramified in aromaticity. Right, that was lesson 2. Turns out in lesson 3 we're going to be doing that as well. And we're tempted to think that aromaticity is going to take us someplace else, but when we look at the subject of lesson 4, we see it's 1, 2, 1, 4 addition. It turns out I'm going to claim that that's really a consequence of resonance. 1, 2, 1, 4 addition. And that's lesson 4. Be thinking, please, in terms of the big picture as you study. It's going to make things a lot easier for you when you can sort of know where the details fit. Alright, it's the gestalt, I think, is what the psychologists call it. Alright, so lesson 3 is the purpose of this video, and it's got 5 objectives. 5 objectives. Number 1, use Frost circle to predict aromaticity. Not my favorite way, but people ask us to do it, so we're going to learn it. My favorite way is to simply use the criteria we had before. I think we can almost always predict aromaticity even without Frost circle. But anyway, we're going to learn how to do that for a sort of simple set of questions, not anything really elaborate. Objective 2 is to identify conjugated dienes and understand how the resonance enhances stability. Objective 3, explain why single bonds in conjugated dienes are shorter and stronger, which you sort of touched on yesterday with the amino acid example. Objective 4, predict the relative stability of allylic and benzylic carbocations. And objective 5 is describe how delocalization of electrons affects pK, which we touched on with that example. Right? That was the point of that reaction. Okay, so those are they, and let's start with the Frost circles. Frost circle. Actually, you know what? I'm going to skip for the purpose of this video. I'm going to skip that. I'm going to let you look at the book for that. It's sort of simple. We've got a fairly small set of problems that we will be asked to do with respect to that. I may come back to that one and do another one later. But for now, let's talk about identifying conjugated dienes. So a conjugated diene is a diene, first of all. There's a conjugated diene, and it's conjugated because we have an uninterrupted system of unhybridized p orbitals. Okay, so this is sp2 hybridized, this is sp2 hybridized, this is sp2 hybridized, and this is sp2 hybridized. That is that carbon, that carbon, that carbon, and that carbon. So this is uninterrupted conjugated diene, and it enhances their stability because of resonance. Okay, so this exhibits resonance. And by the way, these arrows right here are just meant to sort of represent the unhybridized p orbitals. So as I've drawn it, if I've got a pi bond right there, I've got overlap between those pi orbitals, right? And that's what the pi bond looks like. Please review your book for that. Any picture is going to be a little bit deceiving. Okay, so the resonance, though, that this can undergo, you know what? You should pause the video here at this point and predict the resonance. Let me suppose you did, and I'm going to come over here and say these electrons can go here. If they do, of course, they're going to push those ones away. Because if these go here and don't push those ones away, you're going to have 5 pairs of electrons on this carbon right here, and you will be breaking the rule. And I will jump up on that cabinet and point to that periodic table at my own risk of, at the risk of my own life, and scold you by pointing at the periodic table and screaming or something like that. So you tell me now, what is the structure that's over here? I'm going to leave that as an open question. Now, if this thing undergoes, and here's the second open question. There's one. And question 2 is, you know where I'm going here with this, right? What is the bond order of this bond? Okay, that's question number 2. And I'm going to say we've just accomplished objective 2. All right, can you see, by the way, how that fits into lesson 1? I would argue and it's also going to fit into objective number 3, which is Objective number 3 was explain why single bonds of conjugated dienes in conjugated dienes are shorter. Why are they shorter? Because let's use this 1, 2, 1. Let's see, 1, 2, 3, 1, 3 butadiene. Let's use that as an example. This actually has some double bond character right there, right? I guess I just touched on that question right there. This has some double bond character. There are two things we can get from that. Number one, it is shorter, stronger than a regular single bond. And number two, it has some resistance to rotation. Can you see why that is? The resistance to rotation. I touched on that yesterday with the peptide bond. Like the peptide bond, it has a resistance to rotation. How much resistance to rotation? That's an open question. We're not going to go that deep in this comments right now. We can certainly talk about that, but that's not the main point here. The main point is it has some double bond character because of this structure right here. It has some double bond character, therefore it is shorter and stronger, and it has some resistance to rotation. We'll talk tomorrow about the implications of that. Okay, objective 4. Objective 4 is to predict the relative stability of allylic and benzylic carbocations. And I'm going to open up the book to look at that. Let me pause this for a second. Actually, I'm going to set up another video. I'm going to stop this video here and start the video for objectives 4 and 5. Give a separate video for those.